Today until the lunch time, I will cover two miscellaneous topics. Okay. One is on synthetic antiferromagnetism, because we will encounter this a few times in the later part. Then second concept that I will teach is thermal stability. Okay. So, these topics we will touch today. Then tomorrow onwards we will start learning about MRAM. How do we write information, how do we store information, how do we read information in MRAM. So, all those things we will start learning from tomorrow. Okay. So, the first concept we are going to learn today is synthetic antiferromagnetism. So, we learnt about ferro and ferrimagnetism. So, in ferromagnetism we learnt that the neighboring moments will be parallel to each other and J is positive, and this is an ordered magnetic system. And in ferrimagnetic system we learnt that J is negative. So, the neighboring spins are anti-parallel, but they are of different magnitudes. So, there is a net magnetization. Okay. So, this is something that we already learnt. We also learnt about antiferromagnetism, which is also ordered magnetic system. Neighboring spins are anti-parallel and their net magnetization is 0. Okay. So, we also have learnt about their use in exchange bias. So, we learnt about spin valve. So, in spin valve we want to keep the magnetization of one particular layer in one direction. So, we keep this ferromagnetic layer in proximity to antiferromagnetic material, and we follow certain recipe to achieve this exchange bias. Okay. All these things we have learnt. So, what we are going to learn today is synthetic antiferromagnetism. What is synthetic antiferromagnetism? Okay, so, when we say synthetic antiferromagnetism, I mean by the word itself, synthetic means it is not real antiferromagnetism, but we are somehow synthesizing a kind of antiferromagnetic system. Okay, so, in this system what we do is we have two ferromagnetic layers Fm1 and Fm2 separated by some spacer layer like ruthenium, iridium and so on. Even if you remember the GMR concept that we learned, so when we learnt GMR, we learnt that in iron, chromium, iron, the magnetization of the two layers at remnant were in the opposite direction. Okay, so, that is a form of synthetic antiferromagnetism. Okay. So, when we are talking about synthetic antiferromagnetism, we are talking about two or more magnetization in anti-parallel direction. Okay. So, this is different from the antiferromagnetism. So, antiferromagnetism, I mean if you take a antiferromagnetic material, apply some field, let us say 1 Tesla field. So, with 1 Tesla field you will see that the magnetization is almost close to 0. Okay. With 1 Tesla field you cannot do anything, the magnetization of the neighboring atoms are still anti-parallel, the neighboring magnetization is 0. Okay. Whereas, in the case of a synthetic antiferromagnetic material, let us say at remnants maybe the magnetization can be 0. Let us say if the magnetic moment of this layer and the magnetic moment of this layer are the same, magnetization will be 0 at remnants. Okay. But if you apply a high magnetic field, we can make both the layers pointing in the same direction. So, if you remember the GMR, we applied certain field like 2 Tesla, then we forced the two magnetization to be parallel. Okay. So, we can do that. So, in this case the magnetization can be very high. Okay. So, in synthetic antiferromagnetism, we are creating some form of antiferromagnetism by taking 2 or more ferromagnetic layers and separating by some spacer layer. So, because of this spacer layer, the neighboring layers are aligned in anti-parallel direction. Okay. Okay, so it's artificial arrangement. Okay, that's why we have the name synthetic. So, artificial arrangement of magnetization in anti-parallel directions at resonance. Okay, so at zero field. So, this kind of materials can be formed by depositing two ferromagnetic layers close to each other in the presence of a spacer layer that separates them. So, this spacer layer can be ruthenium, iridium and things like that. So, I mentioned that if the magnetic moment of these two layers are identical, then the net magnetization can be 0. But if say one layer is thick, another layer is thin, okay, and if they are arranged in anti-parallel direction, we may have some net magnetization. Okay. So, is full or partial cancellation. Okay. So, when they are like almost equal thickness, the magnetization of one layer will be completely cancelled, you will have 0 magnetization, that is full cancellation. If one layer is thicker than the other layer, then the magnetic moment will be partially cancelled. Okay, so, for synthetic antiferromagnetism, we need at least 3 layers, So, you should have one ferromagnetic layer, one spacer, another ferromagnetic layer. So, let us say if you want to deposit a SAF structure, how many targets at least you need? At least 2, yeah. So, you can use the same ferromagnetic layer, for example, say iron, chromium, okay, something like that, or cobalt, ruthenium, something like that. So, you need at least 2 targets and at least 3 layers to make a synthetic antiferromagnetic structure. Okay, so, quite often people may get confused. So, here I summarize everything, compare everything. So, when you are talking about antiferromagnetism, you are talking about atomic magnetic moments being antiparallel. Whereas, when we talk about synthetic ferromagnetism, we are talking about magnetic moments of layers. Magnetic moments of ferromagnetic layers. Okay. So, when we talk about synthetic antiferromagnetism, we are talking about antiparallel alignment of 2 magnetic moments of 1 or 2 ferromagnetic layers. Okay. So, when they completely cancel each other, we can call them synthetic antiferromagnetism. And if they do not cancel each other, some people call it synthetic ferromagnetism, but loosely everyone calls both as a synthetic antiferromagnetism. Whether you cancel the net magnetic moment or do not cancel, people sometimes loosely call everything as synthetic antiferromagnetism. So, in antiferromagnetism, the interaction itself detects, interaction itself is like J is less than 0. In synthetic antiferromagnetism, we use certain layers that give rise to this kind of interaction. Okay, let me erase this one. Okay, so in antiferromagnetic material, the interaction between two magnetic moment is determined by the exchange interaction, which is less than 0. But in synthetic antiferromagnetic material, we are using layers where J is greater than 0, because these are all ferromagnetic material, right. Okay, so as I mentioned a few minutes ago, the origin of synthetic antiferromagnetism starts from the discovery of giant magnetoresistance. So, the discovery by Albert Furt's group, they found out that at 0 field, the two ion layers have antiparallel magnetization, but when they apply sufficiently large magnetic field, they can force them to be in the same direction. Okay. So, this is one of the earliest observations of synthetic antiferromagnetism. And similar results were also reported by Professor Peter Grunberg. Okay. They also observed similar behavior, but in system where they have only two ion layer. Okay, so this we have already seen. So, after this study was reported, this scientist called Stuart Parkin, he did a very systematic study of inserting various spacer layers between two cobalt layers. Okay. So, if you look at this paper, you will see that he has used around 40 spacer layer, for example, around 40 layers. So, he studied the exchange interaction between the two cobalt layers separated by various spacer layer materials, and they observe this kind of oscillation in the resistance or saturation field. Okay. So, you can notice that when the ruthenium thickness is varied, the saturation field is oscillating. So, what it means is that for some thickness, for example, let us say this A, B and C, you will have anti-parallel alignment of magnetic moments between the two cobalt layers. However, if you look at points D and E, so in points D and E, the two ferromagnetic layers have same magnetization direction. Okay. So, what it means that the synthetic antiferromagnetism is observed only at certain thicknesses. So, thickness A, you observe this, the thickness value of B and C, you observe this, and D and E you do not observe. Okay. So, depending on the thickness of this layer, only certain thickness you will observe the antiparallel coupling. Okay. So, that is the oscillatory behavior. So, some other thickness you may have like milder values of coupling. Okay. So, from this study through such study, okay, maybe let me explain what is this saturation field. So, at resonance, the two ferromagnetic layers are antiparallel. So, when you apply a very large field, the two layers will point parallel to each other. Okay. So, that field where the field at which the two layers have parallel magnetization is called a saturating field in this case. Okay. So, when the saturation field is very large, what it means is that the anti parallel coupling between these two magnetization is very strong. Okay, so, when this coupling is very strong, we need very large magnetic field to overcome this coupling to produce the parallel state. Okay. So, that is the meaning of the y axis in this picture. Saturation field is large means the coupling is very strong. So, at this thickness the coupling is not that strong. A and B, the coupling values are not that strong, but when you go somewhere here, the coupling strength is very large. Okay, so, this is one observation then they made, and so I told you they studied like 40 different material, out of which they found ruthenium and iridium to have the high synthetic antiferromagnetic coupling. For example, let us say this is ruthenium, right. In case of ruthenium, they find something like this. If you do iridium, maybe it is even larger, something like this. Okay. I am roughly drawing to give you some perspective. Iridium has been reported to have very large exchange coupling compared to ruthenium, and compared to this other materials are much inferior. Like let us say you take copper for example. In the case of copper, maybe this coupling is like very weak. Okay. So, after this study, people have used ruthenium as one of the main layers to introduce this synthetic antiferromagnetic coupling, but in the recent past, the MRAM companies, the companies that make MRAM, they also start using iridium, because iridium gives even large exchange coupling. So, this SAF is very useful. Okay, it is not just a physical observation which is useless, but it has lots of use. Okay. So, I will show you a few uses of this synthetic antiferromagnetism. Let us say we go back to our spin valves. So, in spin valve we learnt that we have an antiferromagnetic layer, we have a ferromagnetic layer which is pinned in one particular direction, then we have a spacer layer, then we have a free layer. Okay, so, whenever I draw an arrow, you can imagine that this is like a magnet, right. So, you are magnetizing a material in one particular direction. So, this is like a tiny magnet. So, you know that magnets will generate a magnetic field. Okay, so, this layer will generate some magnetic field. So, this magnetic field will influence the magnetization direction of the free layer. Okay. So, for example, this is north pole. So, preferably having south pole here is more favorable, okay, because you know like when you have two magnets, if north south and south north are like in contact, that is more stable, right. So, if you magnetize this layer in one direction, this magnetization, I mean north south, this is favored, whereas the other direction is not favored. Okay, so, if you have only one reference layer, a fixed layer, a pinned layer, if you have only one pinned layer, it generates a stray magnetic field, and that stray magnetic field only one favors one particular magnetization direction than the other direction. Okay. So, this is the problem. So, people try to overcome this problem by splitting this one layer into a synthetic antiferromagnetic layer like this. Okay. So, instead of one ferromagnetic layer like what we studied before, now we have two ferromagnetic layers separated by ruthenium. Okay. So, because of the ruthenium, these two layers will have antiparallel magnetization. So, now if you look at the stray field from this particular layer will go here, and the stray field generated by this layer will go here, and none of this stray field will go to the free layer. Okay. So, now free layer is not affected by the stray field of the pinned layer. Okay. So, whether in MRAM or spin wall, the reference layer or the pinned layer is now always based on synthetic antiferromagnetism, because we do not want any stray magnetic field to come from this layer. Okay, so, this is one real life use of synthetic antiferromagnetism. The second use is in recording medium. So, in some earlier form of recording medium, longitudinal magnetic recording. So, people used this instead of one recording layer, they used recording layers, two recording layers with a separated by ruthenium. So, they have antiparallel coupling. Because of that, there is some use which we do not go into detail. Then another use also is in perpendicular recording medium, where they again they divide a ferromagnetic layer into a soft magnetic underlayer, and that helps in reducing the noise from the recording medium. Okay. Okay, you do not need to go through this detail, because we are not studying recording medium, but you can just simply appreciate that synthetic antiferromagnetism is also used in recording medium to reduce the noise from the recording medium. Okay. This is another application. So, similarly, when we learn MRAM, I will introduce that we are also using synthetic antiferromagnetic structures in MRAM. So, today I will not go through this, but when we learn MRAM, we will go through this. Okay. But just remember that synthetic antiferromagnetism means we have two ferromagnetic layers separated by ruthenium, which induces antiferromagnetic antiparallel alignment of magnetization. Okay. So, just remember this when we learn about MRAM. Yeah.
How does this layer ruthenium or iridium is facilitating antiferromagnetic coupling between the two layers? I mean, what is the mechanism?
How does it introduce? Okay. I mean, long ago there was a theory called RKKY. So, this theory is from 4 scientists: Ruderman, Kittel, Kasuya, something like that. There are 4 scientists. They came up with a proposal that let us say you have some spins when they are mediated by some non-magnetic material. So, okay, here there is no arrow. Through some non-magnetic layer, they can still have some interaction, and depending on this non-magnetic layers material and the spacing between them, you can have oscillatory coupling. So, these two spins can have parallel coupling or anti-parallel coupling. So, which will be something like this, which you saw in some few slides ago. Okay. So, there is this model called RKKY to explain why this is happening. Okay. So, if you want to know more, you can Google RKKY and understand this model.
So this double exchange interaction or something is a part of this RKKY?
Double exchange interaction is different, right? You are talking about
in the SAF,
Mhm.
the two ferromagnets are like in the antiferromagnetic coupling.
Mhm.
So they are communicating by some mechanism in between because of the spacer layer.
Mhm.
So what the happening. So is that double or the super exchange interaction something happening?
No, it is not double or super exchange. I think you read about RKKY, then you will understand. Okay. Okay, so if you have only one ferromagnetic layer, we know that the hysteresis loop will be symmetric with respect to the center of the MH loop. But when you have two ferromagnetic layers separated by ruthenium, for example, let us say this is their ground state. Okay, in the absence of field, let us say this is how they are supposed to look like. If you measure the hysteresis loop of such a sample, it may look like this. Okay. So, at very high field, the magnetization of the two layers are parallel. When you come closer to 0, the exchange coupling between the two layers makes this one of this layer to flip. So, you will see that the magnetization drops here. So, this is the region at which this magnetization flips from pointing up to down. Okay. Then when you go further, then both layers again point in the same direction. Okay. Then again you go from this side to the other side. This is retained in the same direction, but this layer, the blue layer, flips. Then when you go further, both layer flips in the same direction. Okay. So, typical SAF samples will have some behavior like this. At least one magnetization will reverse before the 0 field. Okay, so you can measure the strength of exchange interaction by measuring a minor loop. Okay. When I say minor loop, what I mean is, like, you start from here, for example, you go all the way, this layer has flipped, let us say you stop at this point, then go back, then you will see something happening like this. Okay, so this loop is called minor loop. Okay, so here you see the minor loop, real minor loop. So, the center of this minor loop has shifted from 0 field by a certain magnetic field, and this is what we call as exchange field. Okay, so this exchange field is related to J. J is the coupling introduced by this spacer layer. So, for example, if you have ruthenium, ruthenium introduces certain J that forces the two magnetization to be antiparallel to each other. So, this is the J, and MS is the magnetization of this particular layer that switches, and T is the thickness of that particular layer that switches first. Okay. So, if you know the MS of this material and its thickness, and you measure HEx by doing minor loop, you can calculate the interaction strength. Okay. So, this is how we calculate how much the exchange interaction produced by spacers like ruthenium or iridium. Yes.
Minor loop in the sense that it has it's leaving only, or sometimes if the loop is not closed, we say sometimes.
Yeah. So, basically if you go from saturation, a very large field that saturate all the layer, to another side saturation, then come back to saturation again, that is a major loop. Okay. But if you do not do that, then that is a minor loop. Okay. Let me give you some example. For example, you have a piece of magnetic material. If you apply very large magnetic field, you will have some hysteresis loop like this. Okay. Let us say this is 7 Tesla. Okay. But in my lab, let us say I have a magnet with only 2 Tesla magnetic field. Okay. So, if I measure this same sample using 2 Tesla magnetic field, so I may go from here to here, then I cannot go beyond 2 Tesla, then I will come back and I will see something like this. Okay. You see that it's not saturated. So, only when you apply 7 Tesla this loop will get saturated, but here I am applying much smaller field which is not enough to saturate. So, I get some, still I get some loop. So, this is called a minor loop. So, in this case again we are going from saturation, but we are stopping somewhere here, right. We are not going all the way to the other side. So, this is called a minor loop. So, someone asked me during the GMR why with chromium, different chromium layer thickness. So, if you remember the GMR curves, they are saturating at different fields, right. So, for chromium 18 the saturation happens somewhere here, chromium 12 the saturation happens somewhere here, chromium 9 the saturation happens here. That is because with respect to the chromium thickness you may have some oscillatory coupling. So, maybe some of them are here, some of them here, something like that. So, depending on the thickness you will have larger or smaller exchange coupling. So, maybe 9 is here, 9, 12, let us say this is 9 angstrom chromium, 12 angstrom chromium is here, then 18 angstrom chromium is here, something like that. So, in this particular set of samples, luckily they are, all these samples are in the same with a positive negative J, which can introduce antiparallel magnetization configuration. Okay. So, with that let us move on to the second topic.
One is before breaks from Sujan Rawat. In GMR device, if thickness of ferromagnetic layer is more than the mean free path of the electron, how does this affect?
Then you, I mean, first question, Pooja Narwat, if the thickness of the ferromagnetic layer is more than the mean free path of electrons, maybe your GMR will be reduced. So, the GMR effect will be reduced as you keep increasing the ferromagnetic layer thickness more and more. So, beyond certain value you may not be able to observe GMR.
Other question is after what properties should have a materials to use as a special layer?
Yeah, this one is difficult to say, but as I mentioned in 1990s itself Professor Stuart Parkin, he has studied 40 different materials. So, from which ruthenium and iridium are known to be a good material. So, why you want something else? Just use one of them, ruthenium or iridium. Okay, so the next concept that I am going to introduce is thermal stability. So, this is completely in contrast with what we learnt early in the morning. Early in the morning you learnt very hard theories, Now we are just going to listen to some story, okay, because it's lunch time. I don't want to teach you hard subject. Okay, so I am going to introduce you to the concept of thermal stability by showing the progress of magnetic recording technology, because as I told you many times before, magnetic recording technology is the parent home from which everything for MRAM came about. So, when we learn about thermal stability of MRAM, again the concepts come from recording technology. Okay, so we learnt all these things. Some of these things I skipped. Okay, so when you want to make recording media better and better for high densities, basically what we do is we make the grains that store the information smaller and smaller. So, you see the diameter is getting reduced, the height is getting reduced, and so on. Okay, let us start from here. So, the hard disk technology was introduced in 1956. At that time, the hard disk looked like this. This whole piece, which people use some heavy equipment to move the hard disk drive, or the hard disk drive that could store 5 megabyte. Okay. But now we can easily have hard disk drives with 5 terabyte capacity. Okay. You can put them in your pocket. So, from this size we have come to this size, and from 5 megabyte we have come to a capacity of 5 terabyte, which is 1 million times larger. Okay. So, this is the growth that has happened in the hard disk drive. So, I always tell how much we have miniaturized everything by using this example. Okay. This example I created in 2000s, but at that time this was the tallest building in the world. Okay. So, this is called Petronas Tower in Malaysia. So, when you compare the bit length of a hard disk drive in 1956 to the bit length of a hard disk drive now, the scaling, I mean the reduction in the bit length is like shrinking this whole tower to this size. Okay. Imagine the miniaturization of a tower as tall as Petronas Tower to this small size. Okay. So, that much miniaturization has happened in the bit length. Okay. So, similarly, you take the width of the track. Width of the track, let us say it was as wide as this Petronas Tower, the first hard disk drive. Now, it is this size 1 inch. Okay. So, this much miniaturization has happened. Because of that, now we have like very high density hard disk drives, because we can pack more bits. So, the price that we pay for every gigabyte was falling down, and so on. So, this kind of growth happens in two ways. One is called scaling, another one is called major technological jumps. Okay. So, when we say scaling, what do we mean is like, let us say these are the bits of say technology in 1980s. So, the bits are this length and this wide. Then let us say we create another technology in 1985, we have made the bits smaller in length and width. As we move further, we make the bits even smaller and less wider. Okay. So, this kind of progress is called scaling. So, you reduce the bit length, you reduce the track width by certain percentage, then we call it scaling. Okay. So, scaling looks simple, but it is not easy. Okay. So, to achieve this, you need to make the grains smaller by certain size, you need to increase the coercivity, the material property you have to improve, and so on. So, you do so many things, then you can scale the bits smaller and smaller. So, to give you some perspective, this is some very old technology where the bit length was 200 nanometer, this one is 200 nanometer, and this width is 2.5 micrometer, and you can measure this kind of bits using MFM. Okay. So, this was possible before 2000. So, mid of 1990s you can measure the bits using MFM, but in current technology this length is only 10 nanometer and the track width is only 40 nanometer. Okay. So, 10 nanometer is even beyond the resolution of MFM. You cannot use MFM to visualize the bits like you did in the past. Okay. So, this is the kind of growth that is happening. So, that growth happens by reducing the grains smaller. Okay. So, let us say in technology, one particular technology your grains are this big. When you move to another technology where the bits are small, you make the grains smaller, even smaller. Okay. The diameter of the grains getting reduced. So, this is one real life example. So, suppose I look at the grains of this technology. So, you store 7 gigabit in a square inch. In this technology you can see the grains are bigger, but if you go to another better technology you can see the grains are smaller, very well separated and so on. Okay. So, if you look at the history of grain size, so this is the increasing areal density. As you pack more and more bits, you can notice that the grain diameter keeps reducing. Okay. We are reducing the diameter of the grains as much as possible as technology grows. So, in recent hard disk drives you can find 15 trillion grains in a square inch. Okay. So, in 1 square inch, which is this small, okay, within this area you will find 15 trillion tiny grains in a square inch. So, that is the progress that we have, that is one thing. Secondly, I told you briefly about pulse width, this also we need to reduce. So, to reduce pulse width we need to reduce the MR multiplied by thickness. So, in this picture you can see that this MRT has been reduced. So, this is typically reduced by reducing the thickness, okay, and coercivity has to be increased. So, all these things happen. Okay. So, basically scaling means reducing or increasing certain parameters. So, reduce MRT, increase coercivity, reduce grain diameter. So, all these things have been happening in the hard disk industry. So, what is the implication of this? Let us get this. So, there is some implication. Okay. So, what is the implication? I will tell you after telling this story. Okay. So, we all claim that chess was invented in India, right, but Russians claim that chess was invented in Russia. So, this story happens in Russia, okay, because this is written by someone else. Okay. So, in this case the person who invented chess, he goes to the king and describe him the game of chess. The king was very happy. Okay. So, the king asked, what do you want? Then the person who claimed to have invented chess, he tells the king that I want 1 wheat grain for the first square, then 2 for the second square, 4 for the third square, 8 for the fourth square and things like that. So, it is going in 2 power 0, 1, 2 like that. Okay, then the king thought this is very simple, then he ordered his people to go and offer this price. Okay. So, a few months later the people come and complain to the king that we do not have any more stock of wheat grains to give it to the inventor of chess. Okay. So, that is because of the way exponential power or 2 power something happens. Okay. So, if you go to the 64th square, right. You will need like 2 times 10 power 19 grains, which is like 1.2 times 10 power 15 kilogram, which is actually more than the worldwide production of wheat. Okay. So, obviously, that kingdom cannot deliver their promise. Okay. So, the moral of the story is, like anything, any technology or whatsoever, if you go from the first board, I mean first square to say somewhere in the middle, you can climb, but after that you will get, it will get tougher to climb. Okay. So, it happened in semiconductor technology. So, Moore's law enabled doubling of transistors, but now we have reached a place where it is difficult to go from say even the 32nd square to 33rd square. Okay. So, that is tougher. So, in the similar sense, hard disk industry also has grown from say like 5 megabyte to around 5 terabyte now, but now we have lots of challenges. Okay. So, to go from 5 terabyte to 6 terabyte itself will be very, very challenging. Okay. So, that is because we have been like shrinking the diameter of the grains. So, from like 50 nanometer we have come down to around 8 nanometer, or we can shrink from 8 to 7 or 7 to 5. That is very challenging, that is one thing. So, we have been shrinking the diameter of the grains, and we have been reducing the thickness of the grains. So, you can notice that in a low density hard disk drives, these grains which store the magnetization have a larger volume, and here you can notice that the grains have a smaller volume. So, we learnt that the energy barrier that keeps the information stable is proportional to KUV. Okay. So, you can notice that the KUV, I mean if you keep the KU same, for example, you use the same material for example, then the volume has gone down, which means KUV has reduced a lot as we progress towards certain direction. Okay. So, that results into a problem called thermal stability of magnetization. Okay. So, in this case I mean this is a cartoon image, not a simulation. Okay. So, I am just using some kind of cartoonist illustration of what happens to the magnetization. Okay. I apply a magnetic field along this direction and saturate the magnetization of these materials along this direction. Okay. So, let us say this is the cobalt cube. So, in this case is a 13 nanometer cube, 10 nanometer cube, and so on. Okay. After I saturate, I remove the magnetic field. Okay. I observe the magnetization at 0 field. So, you can notice that the 30 nanometer cube retains the magnetization in the same direction, 10 nanometer no problem, but if you look at the 8 nanometer one, it flips very rapidly, and 8.5 nanometer also flips, but not that rapid. So, sometimes it is pointing towards left, and after some time it will point towards the right. Okay. So, this is called the thermal stability of magnetization, because this flipping of magnetization happens based on the competition between KUV and KBT. So, at room temperature we have thermal energy. So, this thermal energy competes with the anisotropy energy. So, as a result, when the volume becomes lower and lower, this becomes smaller. So, this energy can compete and make the magnetization flip as a function of time. Okay. So, when this flip is very, very rapid, then we call that a super paramagnetic. So, a few days ago we learnt about this. Okay, so this is one example, real life example of something I measured myself. Okay, so in this case I take a piece of sample, I put it in the VSM, I magnetize in certain direction. Okay, then I remove the magnetic field and I observe the magnetic moment of the sample as a function of time. Okay, field is 0. So, you notice that the magnetic moment keeps decreasing as a function of time. Okay, this is a logarithmic scale. So, it keeps decreasing as a function of time. Okay, so, this decrease of magnetic moment is because of the competition between anisotropy energy and thermal energy. Okay. So, this was explained by Neil many years ago. So, it is called Neil-Arrhenius decay, where if M0 is the magnetization at a time t is equal to 0. So, this magnetization will decrease as a function of time. So, at time t, the magnetization T of that magnetization M of that material will be given by this formula, okay, where tau is given by this one. Okay, so, we can see the anisotropy energy coming here, thermal energy coming here. So, this ratio, if this ratio is large, for example. So, if this ratio is large, this number is going to be large. So, if tau is large, this number is going to be small, then magnetization will not decrease much. Okay. On the other hand, if tau is small, I mean if KUV by KBT is small, KUV by KBT is small, tau will be small. If tau is small, this whole thing is going to be large, then exponential minus some large number means magnetization will decay drastically. So, that is what you see here in the previous image. So, this is a logarithm, I mean kind of, it is not a linear scale, right. So, you see that the magnetization decreases because in this case KUV by KBT is small.
Sir, here it's only based on the time, right? The axis, the magnetization is only a function with respect to time only, right?
Magnetization is observed as a function of time.
Time.
Yeah.
The spin is trying to relax only.
Yeah. Okay, so in that particular sample, the KUV by KBT was small. So, tau is small and we see M decaying as a function of time. Okay, so this is the concept that leads to superparamagnetism, which we already discussed before. For example, if we have a collection of ferromagnetic particles and if they have very large KUV by KBT, then there is no time dependent magnetization decay. So, all the magnets, suppose you magnetize them north, up, south, down, something like this, they retain their polarity. So, even if you observe them after 1 year, they will be still pointing in the same direction. Okay. On the other hand, you look at these particles, they are small. So, their volume is small. So, KUV by KBT of these particles are going to be small, and temperature influences the magnetization. Okay. So, some of them have retained, I mean we cannot say retained, some of them point in the direction, but you can notice that several of the other grains have flipped the magnetization. At another point of time, you can see that they have flipped. Okay. So, as a function of time, the magnetization of these particles will keep flipping as a function of time, especially when KUV by KBT is low. Okay, so that is why I mentioned that the red curve here, the red curve that you see here is the curve of a super paramagnetic system, and the black is the hysteresis loop of a normal ferromagnetic material with a large KUV by KBT. Okay, so, when we talk about paramagnetism, so we are talking about a competition between KBT and the magnetic moments. Okay. In the case of super paramagnetism, it is the competition between KUV and KBT. Super paramagnetism? Yeah, you might okay, let us say you have certain piece of sample. So, at room temperature you have this hysteresis loop, okay, super paramagnetic, but if you go to low temperature, let us say 4 Kelvin, the same sample may show some hysteresis loop, okay, because you are reducing the temperature, right. So, KUV by KBT. So, if you are reducing the temperature, denominator is lower. So, KUV by KBT will be larger. Okay, let us say at a T is equal to 300 Kelvin, KUV by KBT is 15, let us say. Okay, if you make this temperature to be 3 Kelvin, you notice that this gets larger, right. So, at a very low temperature, the super paramagnetic particles will open up, the hysteresis loop will be there. So, room temperature no hysteresis loop, but at low temperature you will see some hysteresis loop. Okay, so here I roughly calculated the KUV, I mean for different KUV by KBT, how much of the magnetization will flip. Okay. So, if I wait for 100 seconds in samples up to KUV by KBT of 50, there will be no change in the magnetization, but if KUV by KBT is smaller, then you see the magnetization is dropping. Okay. So, it is like 1% drop, 9% drop. When it goes to 20, almost no magnetization. Basically, here we have super paramagnetism. So, when we design hard disk drive or MRAM, the industry is selling these products to a customer, right. Suppose I sell you some hard disk drive, say you store your thesis in your hard disk drive, and if the thermal stability of the hard disk drive is only 40, then maybe next day you try to open your file will be gone. Okay. But so, we cannot sell a hard disk drive with the KUV by KBT is low. So, when people sell hard disk drive or MRAM, they will ensure that your data is stable at least for 10 years. Okay. So, if you store your data, if you do not touch, I mean you do not do anything, the data will be there for about 10 years. Okay. So, this is the aim. So, if you look at this picture, so when the KUV by KBT is around 60, even after 10 years there is no change in the magnetization. Okay. Beyond below 60, you will notice that after 10 years there is a drop in the magnetization, which is not desirable. Okay. So, usually hard disk drive makers ensure that your KUV by KBT is at least 60, so that your data is stable for 10 years. So, the implications of thermal stability is like as I said before, if your KV by KBT is low, some magnetization will flip and you will lose your data. And in the case of hard disk drive, we are using polycrystalline material. So, some grains may be big, some may be small, okay, there will be a distribution in the grain, right. So, the smaller grains will always flip and you will lose the data. Okay. So, because of all these reasons, people try to achieve KUV by KBT of 60 or more. Okay, so this is the cartoonist video of what happens when you go towards high technology in hard disk drive. If you are going towards higher technology, okay, you make the grain thickness smaller, diameter smaller. As a result, this magnetization is not maintained. You can see some grains are flipping. So, if you make them smaller and smaller, more grains flip their magnetization because of the competition between thermal energy and anisotropy energy. So, there is a limit to make the grain diameter or the thickness too small. Okay, I think we can stop here. So, whatever I wanted to teach you today, I finished. So, we have learnt about SAF and thermal stability. Okay. So, from tomorrow we will learn about MRAM, how do we write information, how do we read, what are the challenges in storing information in MRAM and so on. So, for the question of Moditma, yes, the sample was initially magnetized and magnetic field was removed and the magnetization was measured over time. Yes. Okay, thank you. We go for break, lunch.